Hi, welcome to another Hopper on 6502 video. I've written a C compiler for 6502. For want of a better name, I called it Tigger C, mainly because if you try and use anything else, you're going to be ambiguous versus, if you say tiny C, there's already about half a dozen tiny Cs, and some of them are 6502 and some are not. Anyway, Tigger C it is. We're running on my my single board 6502, and obviously I'm blinking an LED here. This video is probably going to be fairly long, but I'm going to cover the important stuff in the beginning. So if you're just curious about what the project's about and sit through the first 5 minutes, you should get it all. So let's get along with discussing what this language is first. So it's as close to a C language as I'm prepared to go without, making any compromises. I still drag along some of the things I do for some of the things that I've done for Hopper, which I believe are important in a language, like strict type safety. So unlike C, you can't just cast anything to anything. I have basically two rules of thumb for casting. If you can cast from one type to another without losing anything, and by anything I mean in a numeric sense without losing precision, and in the type sense without losing the meaning of the type. So yes, if you've got an integer which is a positive integer less than or equal to 32767, then you can just cast it to a word without a cast. Same with a byte. You can just cast a byte to a word or to an int. If your integer is negative, then you actually have to explicitly cast it. So if it's a constant, the compiler can see that it can be cast. If it's a variable, then it's happening at runtime, so it has to have a cast. And my cast syntax is I use the word as, so casting one thing, so you can say something as word or as int or that sort of thing. And even though bools and chars and bytes are all the same size, you can't just automatically cast between them. You have to use as a cast. Like here, malloc is returning an array of bytes. You have to cast it to an array of char, and that's because they mean different things. A bool is not the same as a byte. A bool means true or false, and I'm strict about bools, just like I am with Hopper. So the if expression, the while expression, the conclusion expression of the for require Boolean types, so you can't put an assignment in there, for example. You can't say if some integer variable. You can say if that integer variable is equal to 0 or not equal to 0. Other big differences from C, the include doesn't actually include header files. There's no such thing as header files. All it does is it takes all the source file, it inlines the source from the include file into one large file, and it only respects the first time you try and inline a file, just like headers do only respect the first time you include a header in C. So the preprocessor makes one big source file, and it keeps track of the line numbers so that the error messages appear on the correct line numbers in the IDE. And it deals with preprocessor symbols like the defines, if def, and all that. Yeah, what else? Local arrays. So if you declare a local array like that, I'm using the actual 6502 stack, which is only 256 bytes. So if you declare a local array, it only takes up 2 bytes on the stack, which is basically a pointer. It automatically calls malloc, and then when the scope for that local is exited, it'll automatically call free. So that's how it doesn't put those on the stack. It puts them on the heap. The only pointers are created by malloc, and they're only they're not of type pointer, generic pointer. They're of type byte array. and that's a sort of a byte array with an inferred size there. Yeah. Function declarations use the func keyword. There's no void, so func followed by the return type. Switch cases like hopper never fall through, so break is only meaningful in loops. All variables are 0 initialized, including blocks of memory. Yeah, there we go. So anyway, this is on the GitHub under Tigger C, the README, and it's got a full definition, full description of how the language works, what the syntax looks like. It supports inline assembly. It supports this pseudo array for the entire 64K of the 6502's memory, so that you can get and set memory like that. I'll show you how that works later. Anyway, why did I do this? So I've written a lot of languages already. You know, I've written a Forth. I've got Basic. I've written the portable runtime for the the minimal runtime for 6502 to run Hopper on the 6502. And I've always favored sort of I've been biased towards size over speed, or simplicity over speed. And it's been bugging me for a while that I haven't actually written a sort of real production compiler. So I wanted to create a compiler that's actually fast, generates fast code. But I didn't want to do all the work. So I took advantage of the fact that I've already written a 6502 assembler and a whole assembler toolchain with optimizer and all that. So whole program optimization, unreachable code removal, dead code removal, all that sort of stuff is being done by my already existing Hopper 6502 assembly toolchain. So all I needed to do was feed Hopper 6502 assembly into that. So all I needed to do was write a preprocessor and compiler for C that generates that code. And initially I didn't write an optimizer here, I just generated 6502 assembly directly. But that made optimization really hard because it's much harder to optimize, a dozen 6502 assembly instructions than it is to optimize, say, 2 pseudo instructions. So I'll get to that in terms of the design of how I did it. Anyway, so I only needed to write these top things, the preprocessor and compiler and code generator for the language, and so that's what this is. So the preprocessor deals with the preprocessor symbols, generates one big file, sends it into the parser and compiler, and then that generates an intermediate code that is very specific to this. Yeah, this took 2 iterations. I threw away the first one and then realized what I needed, and so the intermediate code is very specific to the task at hand, which makes it really easy to optimize with this peephole optimizer, and then feed that into the assembler. Did I achieve my goal of speed? Yes. So these are my usual benchmarks. So you can see I've got them all pre-burnt onto some EPROMs here so that I can save some time in this video. So yeah, they're blindingly fast. So I can just do a quick demo of one of them. Let's do the Byte Magazine Civ benchmark, shall we? So let's go and switch across to this view. I'll pause while I change the EPROM. All right, so I've changed my EPROM. We've got the Civ benchmark in there. Let's connect with our terminal. COM port 15, we're connected, and let's hit the reset button to restart the program. There we go, it's doing the full 10 iterations of the Civ benchmark, and it takes all of 4.5 seconds. So we're running on an 8 megahertz 6502, right? So let's go back here. So that was our 4.5 seconds down here. So way faster than the Hopper one. But the Hopper one was actually already quite competitive. you know, compared to the basics of 1983. So this Civ benchmark is from Byte Magazine, you know, the January 1983 Byte Magazine. So I've been using it a lot. So if you look at the Apple times for basics, they're pretty slow, like 160 seconds versus the 4 we've just seen. But that's not really fair, because this Apple's running at 1 megahertz and I'm running at 8 megahertz. And I couldn't find really good data to sort of compare apples to apples. But just in glancing, I did notice that the very first 8086s that they had back in 1983 were running at 8 megahertz. So these little guys are running on, this is MS-DOS machines and CP/M machines, and this is a 16-bit processor. So in theory, it should knock the pants off the 6502, right? Well, Microsoft C, 6 seconds. This other C compiler, and it's also comparing a C compiler, not a basic, running at 8 megahertz. My machine's running at 8 megahertz, 7.2 seconds. So, Tigger C is faster than Microsoft C was on an MS-DOS machine, 16-bit MS-DOS machine or 16-bit CP/M machine. So did I achieve my goal of, you know, making a fast C compiler, an efficient C compiler? I think I can say yes. You know, I think I did a good job of that. So from a speed point of view, I'm pretty happy with it. Right, so we've seen the Civ benchmark. Knock that off the list. You've seen the blink going there. What else can I show you? Yeah, the Knowles RetroLab benchmark's kind of interesting. Let's do that one quickly. I'm going to pause to change the EEPROM again. All right, I've changed my EEPROM again. We got the Knowles RetroLab sample loaded. Switch back to our terminal, port for 16, and then I'll rerun the program by hitting the reset button. There we go. So you'll notice I've got 2 different versions running, and they give you different answers. And if you look at the second answer here, 7A314, it's because I don't have a way of easily outputting a hex value. But if you put that in the calculator, you can see it's 500500 decimal, this number. So what's the difference here? I've got 2 versions of the RetroLab demo in the same program, and the one's doing 32 bits and the one's doing 16 bits. And this benchmark isn't that great a benchmark. Let's go have a look at it. NRL, I think it's called. Yes, I've got them both in the same file here, NRL and NRL32. Where are we? Hopper, there we go. Get rid of the video. And I just run the one after the other like that. So this benchmark is just a very tight loop. So it's really, and in BASIC, it's just checking how fast your for loop is, because it's written for BASIC. But I've been using it all along with Hopper as well, so I can compare it against how Hopper is. So if we go and look at the graph again, Knowles RetroLab benchmark is over here. Well, the scale's a little bit wonky here, but we've got the times somewhere as well. Yeah, it's in a spreadsheet. I'm not going to bother. It's just, there's an enormous difference between them. Actually, I should go and find the spreadsheet. Let's do that. I'm just going to switch to that while I work on this. Let's switch back. There we go. All right. So let's look at these speeds here. So, because on that graph they were too small. So Knowles RetroLab is 12 times as fast as the Hopper in the 16-bit version and 33 times as fast in the 32-bit version. While we're here, the Byte Magazine Civ is almost 20 times as fast as Hopper, and the Fibonacci is about a dozen times as fast. And yeah, So the big disparity here is the long versus 16-bit, and both between. If you look here, it's pretty dramatic. Like only a tenth of a second to do the benchmark for 2-byte integers or words, 2-byte unsigns, and then 4-byte unsigns are taking a hell of a lot longer. Yeah. So that's why if you look at the benchmark figures online, it's a little bit difficult to understand what the various basics are doing, like which ones of them are coming up with which of those two answers that we saw on the screen, because you don't get the same answer if you actually add 32-bit values versus adding 16-bit values and having them wrap around. But this becomes incredibly efficient. And the difference between Hopper and Tigger C is here I'm using a 4-byte array for the long value. So I don't do, whereas in Hopper, 4-byte values, it's got a 2-byte stack slot. So 4-byte values are reference type. So when you're trying to do this in Hopper, it's very expensive. It's like using strings to add values together. So, and it does a copy on write. So when you modify something, it makes a new copy of it and gets rid of the old one. So super inefficient to do longs in Hopper. Whereas here, I just wrote some helper functions. So you can go in. This is all we're looking at. This source code we're looking at here is Tigger C. So inside I've got this set of longs. So I've got a long subtraction and then add a word to a long. So you can see it needs to do quite a lot to process the longs, but even with that, it's still pretty darn fast for this demo. Okay, what about the compiler design? We can talk about that a little bit. I'll just show one more feature before I do that. So let's look at this sample. So initially, you saw the blink example. And normally, what blink is doing is it's got these defines as to port A, port B, data direction B, and data direction A. And these are on the 0 page for the VIA. And the naming and the pin modes is very similar to Arduino. So you're going to have methods that, like, to set the pin to true or false, or to read from the pin, or to set the pin mode to input or output and all that. And it's manipulating those the bits based on those port constants. And then it's using the memory, which is, as I mentioned earlier, a way to access all memory on your 6502. And since all the I/O is memory mapped, this is how I/O will work from Tigger C. This is how it works. So when you saw the blink happening on the early example, it was using this code. But for the purposes of this example, I wrote some inline assembly. And it doesn't have much yet. I probably should. What I would probably do is just include an ASM file here. Would be the easier way to do it, and just have the full features of Hopper 6502 assembly right here. Like it's got ifs and switch statements and things in the Hopper 6502 assembly. Whereas here, I just to implement this quickly, I just put the assembly in a string and made a keyword to emit that assembly directly, like included in the output stream. There's one more thing, and this was Dave's idea. So an underscore starting the name of a function means that this is a so-called naked function. So it means it has no entry code and no exit code other than RTS, which means it has no stack pointer, base pointer manipulation, which means it can't have a return value and it can't have arguments and it can't have locals. But it is also pretty lean and mean to use a function like that. And I'm using them here to turn the LED on and off. So it's just a single instruction. So with the 6502C, you get these, the 65C02S, you get these bit instructions on the 0 page, and my ports are on the 0 page. So I can use these bit instructions to just set or clear a single bit on the parallel port. Rather convenient. So this would, it's not like you need speed to blink LEDs, but if you're implementing, say, if you're bit banging serial or something like I2C or something, this would be pretty handy to be able to write that in C. Yes, let's I'm going to pause and switch to what I'm going to switch to, the Mandelbrot example. Yeah, why not? Okie dokie. We've got Mandelbrot in there now. Let's reconnect our terminal. Port 15, and then I'll press the button to rerun it. So yeah, it's probably about as fast as we've ever seen the Mandelbrot draw on the 6502 for sure, like 8 seconds. So let's go back and have a look at that again. So yeah, there you can see the Mandelbrot times. The oranges are the 6502 and the yellows are the Hopper version of the same time. Yeah, the 32-bit Knowles Retro Lab is very, this is the long I was talking about. Yeah, and then there's one more example that I use other than the Mandelbrot. I mean, Mandelbrot's pretty interesting. We'll go and have a look at the Mandelbrot when we look at code generation, but I want to mention one more sample. So let's go and have a look at the Fibonacci one. So the Fibonacci sample is one that I used to benchmark against Python, against MicroPython, and because I ported it from MicroPython, and there's times available for MicroPython. But it also is a recursive example, like the most evil recursion you can imagine. So it's doing, 24, a depth of 24 recursive calls into this fiber method. Now, I've tried to do, like the Hopper virtual machine. One of the reasons it is slower than running native code is because it's got to manage its own stack. So you can't use the CPU instructions to manage the stack because the stack would just be too limited in that way. So Hopper stack slots are 2 bytes wide. So each Hopper stack is a byte, is a word. But there's also a hidden byte for the type of each stack slot. And that's so that the reference types can be managed properly by the garbage collector. So it knows if it's got a pointer on the stack, it knows what type the pointer is at runtime. So you can have variant types. You don't have to know at compile time what type is going to be there. So that means you've got 3 bytes per stack slot. So if you were going to only use the built-in 6502 stack and you've only got 256 bytes of stack space, those 3 bytes, it gets pretty expensive. I mean, it means your stack depth can never be deeper than 256 divided by 3. And if you're going to put the return addresses on the stack as well, and you're going to put the frame pointers, so the return address would be another 2 bytes, and the frame pointer, because it's only a 256 byte stack, the frame pointer would only be 1 byte. So now you've gone up, so each function call, you'd have 3 byte stack slot for the argument, and you'd have another 3 bytes taken up by the return address and the restoring the base pointer. So 6 bytes per method call. So if you try to do this example, that will be 144 bytes on your 256 byte stack being used for that. Oh, and local variables too go onto the stack. Of course they do. Local variables and arguments. So that's why I couldn't do that for the Hopper code. But for this compiler, I really, really wanted to use the built-in 6502 stack, because if you're manipulating your own stack, it means 3 or 4 instructions at least, instead of 1 to push or pop something from your stack rather than pushing and popping it from the built-in stack. So my C compiler uses the built-in stack for arguments, local variables, obviously the return address, and for storing and restoring the base pointer. So that's why this test is important. So like I said, in this case, it's going to use 6 bytes for the return address, 1 byte for the base pointer. It's going to use those 6 bytes, but it works. It runs just fine on that. It's got it uses a lot less space. Yeah, because on the Hopper stack they all 2 byte slots, whereas these it's only 1 byte for the base pointer and yeah. So and yes, like I mentioned before, it's storing these. If you've got a pointer value, it's storing just the pointer, not the actual. So this looks like a local variable that's stored on the stack. Well, not that one. The other one, the one I showed with digits. So like this kind of thing where you create a 5-character local variable. And it's not really created on the stack. It's done with malloc, puts a pointer on the stack, and then when it exits scope, it frees it again. Anyway, the short version, this Fibonacci sequence I like because it tests whether your stack is actually deep enough to be usable. Right, let's go look at some code generation. And which example will we use? We can use the NRL one. So let's build that. Oh, let's first build it with, if we switch check build, it won't do the peephole optimization. So let's do that. And there's all the toolchain steps showing here. And then let's go and have a look at it. So in the debug intermediate folder, it created nrl .asm. So this is the assembler that the compiler generated automatically. Includes a lot of system libraries that come from the 6502 runtime. I didn't rewrite a heap manager, I just reused the one I had. And even though this looks like a lot of code, the 6502, the Hopper 6502 assembler, the optimizer does whole program optimization, so it only includes methods that you actually use. This resources here, that's the string constants. Yeah, that's an interesting thing too. If you don't use the heap and you only use the stack, you could actually, in theory, run on a machine with very little RAM. So you could possibly run on like Anders Nielsen's 6507, which has only got 128 bytes of RAM. And you could still have strings as long as they're only constant strings, because they're these ones which are in the ROM, they're not in RAM. So if you don't use malloc and free, you only use the stack and the 0 page, a bit of the 0 page. So you'd have to be careful about where your 0 page variables are, shove them all at one end on the 6507 and use the other half for the stack, and you could, the C compiler would actually compile usable code for that platform. All right. The thing I said earlier about optimization, it's really hard to try to optimize this sort of code, like 15 instructions, to try and see what's going on here. Like this push and that pop are obvious. You can get rid of those two because they're a no op. But where does this push end up, or where does that one end up, so that you can optimize away the pop lower down. So much harder to do it this way. So my solution was to generate an intermediate format. So that's what this comment is here. So push immediate byte, remark, push another immediate byte, push a local variable at this offset from the base pointer, add, etc. So let's go have a look at what those mean. So the comments are the remarks, and then push a byte is this here, and then push another byte, another 0 is there, and then push the local variable with the base pointer. So the base pointer is stored, the base pointer for the current stack frame is stored in the 0 page variable. And this calculation here is getting into X, the address on the stack of the local variable. So load the base pointer, clear carry, add the offset, which is +5. It's confusing here. This is the logical offset, but this is the actual offset, because so the logical offset here looked like -2, right? Because it's the local variable. but the actual offset is +5 because the 6502 stack grows downwards. So -2 is going to be a plus direction if the stack's growing downwards, and then it's also got to skip. So instead of being +2, it's +5. Why? Because there's a base pointer stored on the stack from the previous stack frame and a return address. So that's another 3 bytes. So it's +5 instead of +2. There you go. And then put it into the X register, and then load the least significant byte, push it, decrement the X register again because the stack is growing downwards. Most significant byte and push it. So that's pushing a local variable. What does add do? Pops the least significant byte of top, pops the most significant, least significant, most and least of top and next, adds them together, and then pushes the result again, pushes top. So this is, fairly standard code generation if you don't really care about performance and size. Very simple stack interaction. But if you care about performance and size, you would imagine this could be a lot smaller. And we're going to see how much smaller these operations can be. So let's focus on just pushing. We pushed 0, we pushed a local variable, and then we added them together and popped them off the stack, added them together, and pushed the result back onto the stack, right? So it's what my people optimizer does is it optimizes these. It ignores the remarks, obviously. Optimizes these intermediate instructions. So the optimization for this intermediate instruction would be to say, take an immediate value, take a local variable, add them together, and put them back into the local variable. Because it's quite, they're not back into the local variable, they're being used for something else. But often that happens too, so it's even better. Anyway, let's go see what that looks like if we turn optimization on. So we go back in here again, and we go and turn on, say, don't make me check build, and now it's going to optimize that. And this is the peephole optimizer in the C compiler rather than this optimizer here, which is the optimizer in the Hopper 6502 assembler. Let's go have a look at it. So here we are again. So that code got replaced with something called IL add. So what that means is taken, you've got an intermediate value, you've got a local variable, and you want to add them together. And that's the intermediate value, and that's the local variable, and add them together and put it back on the stack. So all that code became that. That's it. So it optimized down, 25 instructions into these instructions here. So, you can walk through it again and see what it does. There's still the expense of calculating the stack position of the local variable. So that's the same, right? But it didn't store it in X and load it, or store it in A, because you can only do this addition in the A register. You can't do it in the X register. So it didn't store it and then load it back into X. It just transferred it to X. And it can do that because it can look ahead and see what's being used. And then it loaded the least significant byte of the immediate, added it to the least significant byte directly. So it's not putting these on the stack at all, it's just doing them directly. But it is pushing the result and then decrementing, loading the most significant, adding and pushing. And in theory, you could optimize this away entirely because that's a 0. But in practice, it's a lot harder than you would imagine to do that. And part of the reason is because this was pushed onto the stack as 2 bytes. And if you push onto the stack in 3 bytes in a row, for example, then the peephole optimizer would take the first 2 bytes and make them into a push of a word, and the third of the 3 bytes would be on its own. So this thing here wouldn't see that single byte is actually a 2-byte operand because it's being broken by pushing. If pushing 3 consecutive bytes, the peephole optimizer has to choose which 2 are a pair, and it doesn't know enough to be able to realize that the first 2 are not a pair and the second 2 should have been the pair. So it's harder to optimize away adding by 0 than I thought it would be. So I stopped doing it because it created too much breakage. But it's more obvious if you look at the add one here. So there you go. And yeah, you could anyway, you could do an increment instead of an add one as well, which I could do probably, but so I could just increment this directly. But since I have to push it onto the stack anyway, I think I do that actually. I think we do increment automatically and put and because if you increment and don't put it back on the stack, it works fine. So we could test that quickly. Let's do that. Let's delete whatever this is. So for and word I actually we can show you just how efficient it is. For byte I equals 0, I less than 2, 5, less than or equal to 255, I plus plus. Right. Get rid of all that. Oh, I can show you something else. Oh, maybe we should just do some output here. Yeah, a good demo of something else that you haven't seen yet. So, write word I. So that should be an automatic cast. Let's see if it works. Yeah, let's see if it's automatically got optimizer on, all that. Okay. So we should turn that off first and compile. I'm going to show you how the emulator works as well using this example. I want to add one more thing. It's going to just, so we should put a right char new line here. Yeah. Okay, let's have a look what that looked like. So edit debug obj test.asm. So it's going to be right at the bottom, I think. It generates a lot of code. There's our right word. There's a right char. Let's go and look at the increment just for see what the increment looks like. It'll be at the end of the for loop. There's the end of the for loop. This is the increment here. Yeah, so actually that's good. So we can remember which line it's on. So around about line 6000. Generates a lot of code. And that's because it's generating code for all the runtime libraries. It only knocks them out in the next stage. So why is it pushing this twice? Right. So it's pushing a local variable of size byte. I'm going to get rid of that. I just noticed that I've still got that in the way. Okay, there we go. So it's pushing the local variable, pushing one, adding it, popping that into the local variable, and then decrementing the stack pointer. So why did it do that? Well, it's because this is I++, and I++ is actually an expression that leaves the value of I before the plus, before the increment on the stack. So that's what the first push is. So the first push is just leaving the pre-increment or post-increment. So it's post-increment. So it's leaving the value of I before the increment on the stack after the execution of the increment. So push I again, push a 1, add it, pop I. And then over here right now, the value before the increment is on the stack. And then that decrement stack pointer by 1 is because we didn't consume that value. We didn't use it for anything, like it wasn't part of an index to an array or something. Okay, so all that code here, is like, you know, starts over there, want all this code here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 instructions, right? So let's go and see how well the optimizer does with that, the peephole optimizer. So we'll turn it on, and this is the I++ we're looking at, right? So it's pushing I onto the stack, it's incrementing I, and then it's clearing that unused I from the stack because you might use it for something, right? Like if we did write word I++, it should write out the value of I before the plus. Okay, let's compile that. And have a look at it. And it was right near the end. This is it here. So the I++ is that. So it took all those instructions and made them into that. So that's like an extreme example of just how good the peephole optimizer is. Right. Anyway, let's see it in action. So we've got an emulator, E6502. Now, the emulator has something called Apple One mode. And I actually had this Apple One on here. So instead of using a serial port for the write instructions, the Apple One mode has display and keyboard features, and I developed this when I made Wasmon work. So we can go E6502 -1 test.asm, and it didn't like that at all. Why didn't it like that? Oh, I know why. I need to be in that folder. And let's try that again. There we go. Now, we're in the emulator. This is a 6502 emulator, but it has a very familiar feel to it if you're used to the Hopper monitor, because it's got the same instructions as the Hopper monitor. So there's our, let's just F5 it to run. And there we go, 0 to 10, right? Our output from our program. And we could go and set a breakpoint. So these are initializing all the memory. Let's put a breakpoint. Let's reload that. Put a breakpoint on 802D. F5 to there. And let's see what the source is at that point. Let's go down a bit. F10, 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 F10. Look at some more source. There's your less than or equal to going on. And these comments are before it was optimized. It's not ideal. There's our right char. Carry on down a bit. And if I F10 over the right char, so we're about to do a right char, we should get an extra character here. There it is. Oh no, that was the line break was the right char. We want the right word. So the right word here should give us a character on the screen. There it is. It's the 0 over here. And then it's popping off that, and here's our increment. About to increment, and we can look at the stack at this point as well. So there's the stack. Return address 0, where you came from. Not a very exciting stack, but if we increment now, we should be able to see, and X is our pointer into the stack. So we should see FC, which makes sense. It's this top thing on the stack. It's the local variable in the 4. It's in the stack frame of the 4, or the scope of the 4. Now, if we look at the stack again, there we've got a 1. So that increment did exactly what we expected. And then branch around to the beginning again. All right. What else can we look at? We can probably do the Mandelbrot in here. Let's do that. Yeah, so let's go TC, edit Mandelbrot. Uncomment this fdef to say, and let's make sure we're optimizing, yes. So we're building the Mandelbrot, but to use the Apple One serial IO rather than the And it's actually not serial I/O, it's just writing a whole byte to a register and reading a whole byte from a register for the keyboard and display of the Apple One, rather than using a serial port. Okay, let's do that again. Let's go back to debug obj and E6502. So this emulator is in the Hopper environment, running in Hopper. It actually can handle a serial port as well. You open two different Hopper windows and use them at the same time. It's like if you wanted to emulate the actual 6502 runtime. This is how I tested the 6502 runtime. So we load up Mandelbrot, and then let's kick it off. So I did this on purpose. The output in the emulator is in blue so that you can tell that you're in the emulator and you're not on the serial port. Anyhow, you can also see that even though this took 8 seconds on the 6502, the emulator, which is all written in Hopper, and it's emulating a full 6502 processor in Hopper, is a little slower than the hardware. Very good. Thank you for watching. I think we can fade out on our there we go. Go switch the desktop. Put our screen back in there and pack it in. If you have any questions about this, let me know. I'll put some playlists at the end to Hopper on 6502. And if you want to get more involved, we do have a Discord server. Just message me for an invite to the Discord server. Thank you for watching.